So we are looking at page 18 of your unit handout here. We're going to be looking at trigonometric proofs today. And I don't know if you recall, but when we first learned about identities, we had a lesson that covered the Pythagorean identities, the quotient identities, and the reciprocal identities. And you had a daily assignment that was tied to that, but then the next day we spent the whole day going over problems and practicing more. That's what we're doing with proofs. So we have a lesson today on proofs. You're going to have an assignment that you should complete for tomorrow. Tomorrow we will go over questions from that assignment, and we will continue to do more proofs. Okay? And the thinking is, the educational philosophy that I have here with this is, you need lots of practice with proofs. Everything we've learned so far is going to go into proofs, but you still need lots of practice because there's so many different proofs that you might have to complete on an exam. So we're going to be proving trigonometric identities algebraically and going back to understanding the difference between verifying an identity and proving an identity. So to begin with here, we're going to be talking more about non-permissible values. And I really ought to have included these three little points in your note package. If you want, you can write them down as I talk about them. At the end, you can take a picture with your phone of the page. It doesn't matter to me. What matters is that you understand what I'm going to talk about. When you have non-permissible values for a rotation angle, they always occur because you end up dividing by 0. That's the only way we get non-permissible values in trigonometric expressions, is the angle that you're taking maybe the tangent of results in division by 0 somewhere. Or you get division by 0 for some other reason. Okay? When you are looking at non-permissible values, we always have to revert back to the concept of x, y, and r. You can go with a unit circle or a non-unit circle, it doesn't matter, but you have to think of x, y, and r. So the final point is this. Even though you may be tempted to simplify an expression, you do not simplify any expressions when you determine trigonometric non-permissible values. Okay? So as a quick illustration, and I don't believe you need to write this down, but if we had a trigonometric expression and it had, I don't know, tangent of x sine of x over sine of x cos of x, I think everybody here understands that you can cancel those sines of x's. But as it stands right now, sine of x is in a denominator, which means sine of x is not allowed to be 0. Now, I'm not worried about what x is not allowed to be. I'm just saying sine of x is not allowed to be 0. That's going to be one of the statements that you end up writing. Another one is going to have to be cos of x is not allowed to be 0. And there's something else in here, but it's covered by those two statements I've just written outside of that funny cloud. Okay. These are not non-permissible values. We would still have to figure out what x is not allowed to be. Okay, and I don't want to get into that right now. My point is, even though these cancel, you still have to say sine of x cannot be 0. Non-permissible values are determined by looking all the time at the original expression. All right, let's get to it. Example 1. And for each of these examples, I've constructed an example that's very similar in the procedure to examples that are in this section in your textbook. So on page 310 of your text, if you have difficulty later on with this example, I hope you don't because I think it's a very basic one. You can take a look at your textbook and their example. Okay? So the first thing is determine the non-permissible values. And I would always recommend rewriting things a little bit larger. In other words, if you have a written response question and you're asked to do something with an equation, rewrite the equation and then get down to the work. So I would also recommend when you're talking about non-permissible values that it's much easier to think about what's allowed and what's not allowed when you're dealing with sines and cosines, but not cosecants and not cotangents and not tangents and not secants. In other words, I'm going to write everything in terms of sines and cosines. And I'm going to double check, because again, you know me, I just get on autopilot sometimes and don't think. But tan of x is sine over cosine, and then I have times cosine. Cosecant is 1 over sine. Okay. So now, the non-permissible values. And I don't know how you want to communicate this on a written response, but I think it has to be communicated. We can write what's not allowed to be 0, but I think you need to show why. And I'm going to choose to do this using highlighters. And then I will show you what I would recommend you do if you're writing an exam and you don't have highlighters. I'm going to highlight things that are not allowed to be 0. Cosine of x, I don't know why my computer is wheezing away this early in the morning, but there it is. I'm going to highlight that cosine of x. And that's going to lead me to this statement that, it doesn't matter where I put this, that this cosine of x is not allowed to be 0. Why? Who can tell me why that cosine of x in that expression at the top of the page is not allowed to be 0? It is a denominator, and I like the way you said that. It's not the denominator. You said it's a denominator. There's a denominator of cosine of x. So the fact of the matter is, and don't write this down what I'm going to write, if cosine of x was 0, then this piece of the left-hand side wouldn't be defined. And if that piece is not defined, the whole thing is not defined. It just falls to pieces. Okay, what else do we have? Well, on the right-hand side of this, we don't have any denominators. But we also have a denominator here. On the left-hand side, we have this denominator. We have 1 over sine of x is not allowed to be 0, because 1 over sine of x is a denominator. The fact of the matter is 1 over sine of x will never be 0 because it's 1 over something, but we'll get to that in a minute. Are there any other denominators in this expression? I'll give you a hint. Yes. What's the third denominator that's in this expression?
Sine of x.
Sine of x. This bottom piece within this bottom piece, that is a denominator. So we have to now say that sine of x is not allowed to be 0. Let me bring this all back so we can see all of these statements kind of all together. That's what we're talking about. And again, these all happen to occur on the left-hand side, but they don't have to. Sometimes there's some on the right-hand side, but there aren't any on the right-hand side here. So now, what are the non-permissible values? When you solve this statement, I don't want to call it an equation because it's not equals, it's not equal to. You ask yourself, where is cosine of x equal to 0? Don't forget that cosine of x, the whole thing is the x coordinate on the unit circle. So where on the unit circle is cosine 0? It's 0 here at the top. Where x is 0, and at the bottom where x is 0. And I'm saying x because it's cosine. And what that tells us is that angle x is not allowed to be pi over 2, 3 pi over 2, 5 pi over 2, but pi over 2 plus multiples of pi. I'm just going to leave out the n being an integer until later. I don't want to crowd my workspace here. On the other hand, when we take a look at sine of a rotation angle being 0, sine is a y-coordinate on the unit circle. So where on the unit circle is the sine going to be 0? Here and here. So now we can write that x is not allowed to be, well, this is 0 and pi, or negative pi and 2 pi. There's all kinds of ways you can write it. Basically, it's multiples of pi. And again, n is an integer, and we'll add that in later. How is that possible? Okay, so we talk about this when we deal with rational expressions. When you have a fraction, if a fraction is going to be equal to 0, the only way that can happen is if the top of the fraction is equal to 0. So 1 divided by any number that's defined, because there are non-permissible values for sine of x, but 1 divided by any allowable number will always give you a non-zero result. So this goes nowhere in terms of non-permissible values. So what are the non-permissible values? They are these four, they correspond to these 4 locations I've got at the top of the screen. So we're simply going to say x is not allowed to be multiples of pi over 2. Because these are all pi over 2 apart in either direction. So rather than saying pi over 2 plus multiples of pi, and also saying multiples of pi, we can just say multiples of pi over 2. And those are the non-permissible values. As we go through more and more of these, I'm going to spend less and less time. I'm going to go into less and less detail on the board. I had mentioned before, what do you do if you're writing an exam and you don't have highlighters? And I really believe this is good advice. I think what you do is something like this. I mean, it's always nice to have a different color pen. If I were you, I would have a different color pen. But I might do something like that, right? The point is you want to make it clear why these statements are true that I've written. Now, one final thing. Again, this middle statement doesn't lead anywhere. Don't, on a written response, just look at it and go, well, that's not going to lead anywhere, and ignore it. You have to address it. Okay. Now we're going to prove this identity. And this is, I would describe this as a very simple proof. The first thing that you want to understand is that everything we've learned to do with identities, we're going to continue to do. The idea of a proof, and we've seen a couple of them before, is that you deal with the left side and the right side, and you demonstrate that they are really the same, they just look different. So the strategy is for you to take one of the sides and make it into the other side, or take the other side and make it into the first side, or do stuff to both sides separately to bring them together. But you never move across the equal sign. In fact, in a proof, you don't even write an equal sign. Now, would you agree that it makes more sense if I had a complicated expression on the left-hand side and a simple expression on the right? It makes more sense to try to turn the complicated one into a simpler form rather than to try to take the simple one and make it complicated somehow? Okay. So I'm looking at this and I'm thinking most of my work is going to be done on the left-hand side. So when I construct my table, my left-right side table, I leave myself lots of room there. And we are going to have the work, the algebra underneath this phrase left side, but we're also going to have room here to write reasons for what we do. The first thing I'm going to do is the first thing that I've always suggested. Write everything in terms of sine and cosine. We already did that in part A of this question, but let's do it again. Okay. So that's what I've done first. And the golden rule is this. Anytime you use an identity to change the appearance of something, you have to write down the name of that identity. So we used a quotient identity here for changing the tangent to sine over cosine. And we used a reciprocal identity to change the cosecant to 1 over sine. Invariably, and this is a math class and I get it, some people go, I can't remember all these words, and that's fine. I'm going to write what you could put instead. I don't think you have to write it down, but if you didn't remember that that's what they're called, I would put over here, instead of this, I would put that. And there's absolutely nothing wrong with that. In fact, I think it's a better thing. But it's quicker to just write reciprocal and quotient identities. But anytime you change the appearance, you need to justify that. Okay, what now? Well, now, and I'm going to make a recommendation here. I'm going to cancel those cosines, and I'm left with sine x on the top over 1 over sine x on the bottom. Now, would you agree that we're going to have to multiply top and bottom by sine of x? Okay. My recommendation is don't do too much at once. If I were working on this alone, I would probably cancel my cosines at the top of the screen and simultaneously write times sine x over sine x. The problem with that is when somebody's marking your work, it's hard for them to follow what you're doing. Okay? So now I'm going to multiply sine x on the top and sine x on the bottom. I wouldn't recommend always using a different color, but if you had a different color pen, I think that's important because it shows the marker that that's something else you've added into the mix. Okay? This cancels, and you're left with sine squared of x. You do not need to justify algebra with words. You only need to justify changing the appearance with identities using words. Now, how many of you see, I'm going to bring the right-hand side down now. The right-hand side was 1 minus cos squared of x. How many of you see they're equal to each other? Okay. Even though it's obvious, we're not done the proof. We either have to write, there's two options here. We either have to say, well, this is equal to 1 minus cos squared of x because of the Pythagorean identity. And then we can say the left side equals the right side. Or you could end it here and take this and write, oh, well, this is sine squared of x, and end that there, write Pythagorean identity on this side, and then say left side equals right side. I kind of, unless there's a lot of complicated simplification that needs to go on both sides, I tend to work just on one side. And that's it. Any questions with that first example? All right, number 2. Oh, we've already done that. What was B? Oh, verify that it's true. I'm not going to do that. I should actually take that out of your notes. If you want to graph this on your graphing calculator for y1 and graph this for y2, you'll see they're equal, okay? Other than the non-permissible values. I don't think we need to do that. Example number 2, prove this identity and state the non-permissible values. Well, let's state the non-permissible actually, you know what? For this question, let's not state the non-permissible values. And this isn't a time issue. It's that we're going to learn something tomorrow that will allow us to answer that question, but you don't know it yet. Okay? So we want to prove this identity. Sine of 2x. So I'm rewriting it over cos of 2x plus 1. This is the left side. Would you agree, just take a look at the identity we're trying to prove, would you agree the left side is more complicated? It's going to require more work. And the right side, is it tan x? It doesn't get much simpler than that. I mean, at some point we might want to say tan x is sine x over cos x, but if we need to do that, we can do that. By the way, and I hope you understand my reasoning here, on the heels of what I just said, I know tan is sine over cos. So if I end up with on the left-hand side sine over cos, I can just write tan x on the left-hand side. I don't have to touch the right-hand side. And my point is, I'm going to leave myself lots of room. I mean, part of math is communicating your work, and you have to be organized to do so in a good way. To organize your work means good communication. What can we do here? Okay, there's only one thing we can do with the sine of 2x. It's that. Now, why am I allowed to do that? I'm allowed to do that because of a double angle identity. And I'm going to write double angle identities, actually, because I'm about to do the same thing with the cosine. So now, I'm going to just, in some space I have up here, write down the 3 double angle identities for cosine of 2x. You don't need to write them down. You should have your formula sheet out and you can see them, but I want to refer to them up here. Cosine of 2, I'm going to use theta equals cos squared of theta minus sine squared of theta. Cos of 2 theta equals 1 minus 2 sine squared of theta. And cos of 2 theta equals 2 cos squared theta minus 1. Did I get them correct? Okay, so my question is this, and to some people, the answer will be immediately obvious. To others, not so much. What is my best option? Which of those 3 should I use to replace cos of 2x with something else? So to how many of you, after that 10 seconds of thought, is it clear which one will work? I mean, you can try them, but first of all, if I look at the first option, if I were to write, and please don't do it, but if I were to write in here cos squared minus sine squared, all of a sudden, I have changed the bottom from a cosine and a number to a cosine, a sine, and a number. Nothing really happens there. On the other hand, if I were to do this, I'm going to end up with 1 plus 1, which is 2, 2 minus 2 sine squared. There's some things you could do with that, but it's more complicated. It's less work if we just put in cos squared, 2 cos squared of x minus 1. Why? Because minus 1 plus 1 is nothing. And all we're left with on the bottom, and this is absolutely crucial, all we're left with on the bottom is a single term, which means everything on the bottom is a factor. 2 is a factor. Cos is a factor. Cos is a factor again. And by the way, double angle identities covers our trigonometric substitution. The question is, how many of you see that that's equal to tangent of x? I mean, now you just have to formalize it. You have to say, and I don't believe you need to do this, but this is 2 sine x cos x over 2 cos x. I'm going to put brackets around all of this stuff to indicate that they're factors. That's not a universal code that a marker in Edmonton is going to look at your work and go, oh, they recognize their factors. It's for you to understand their factors. The 2's cancel. The cosines cancel. I don't need to justify that. And I would, if I were you, just write what you have left here. And then go tan x. What's your reason? You used a quotient identity. And you can write left side equals right side because it does. On the left side we got tan x, on the right side we got tan x. Again, just to do a little review here, you are rewriting it, thinking ahead about what it is you need to do to leave yourself enough room. This was not part of the proof. This was just me explaining the identities and which one of the 3 to use. Leaving yourself enough room on the side that you're going to work on the most. Anytime you use identities from your formula sheet, which you never have to prove, you're allowed to use them, you have to put the reason for your substitution, the name of the identity, or write out the identity. Any questions with 2? Let's take a look at number 3. Again, pointing you to a place on the formula sheet, or not on the formula sheet, in your textbook where there's a similar question. Prove this equation is true. What are the non-permissible values for x? So let's do the non-permissible values for x first. This is not my proof, by the way. I've given you enough room that we can do the non-permissible values and then the proof below it. If I were to rewrite this so that I have all sines and cosines, that's what it looks like. After you write it down, just take a moment to think about all of those changes. I'm not proving anything. I don't need to justify anything right now. Although, when we do our proof, this is going to probably be our first move. Okay? Are we okay with rewriting the right-hand side that way? Okay. So, what is not allowed to be 0? Well, I have this as a denominator, and it appears in multiple places. I would, on an exam, I would indicate that you're seeing it's in 3 places. But I have this statement now, that cos of x is not allowed to be 0. But I also have this. That's a denominator. So sine of x plus 1 is not allowed to be 0. Well, that means that sine of x is not allowed to be negative 1. So when we go to the unit circle, and again, if you're writing an exam, I would recommend taking a coffee cup or something and drawing a decent circle. You're allowed to do that. Where is cosine of x 0? Cosine of x is 0 here and here. Where is sine of x equal to negative 1? It happens to overlap with this one. But if you did this question on an exam and you forgot or ignored the sine of x plus 1, maybe you even ignored it because you knew it wouldn't matter. you would still get the correct two positions for non-permissible values, but you wouldn't get full marks. You have to address the sine of x is not equal to -1. Our non-permissible values are angles that end in those locations, which means that the angle x is not allowed to be pi over 2 plus multiples of pi, where n is an element of the integers. All right, let's prove this beast. And, you know, in retrospect, from a teaching standpoint here, when I wrote 1 over sine of x plus 1, and then I had equals, what did I have? Whoops. 1 over cos minus sine over cos. Over what, Allie?
Cos x.
Over cos x. And I said we're not proving it just yet. In retrospect, I could have just written that and said, let's do our non-permissible values and then we'll get into the proof. So I have the left side and the right side. I don't think you have to write left side, right side, but I'm going to. I hope it's obvious that the side that needs the most help from us is the right-hand side. Algebraically, it's a mess. Oh, that's not the start of the question, is it? So we need to put here the reason why we changed those secants to 1 over coses, right? And I just want to double check because we started this on a different page for me. Is this what we wrote? Okay, so we have to put a reason for that. Algebraically, this is a mess, and I'm going to actually rewrite this. I apologize. I don't think I followed my own advice, which is to look at what you're going to need to work on the most and give yourself the space required to do it. So if I were to go back, if I were to begin again at this stage, I would have done this. And I would have left myself more room on the right-hand side. I don't think I need to do that. I'm going to multiply top and bottom of this by cos x. To clear those mini denominators. That's always what we want to do with a messy fraction. As I said, algebraically, this is a mess. When I multiply that cos x through on the top, I get 1 minus sine x over cos squared of x. When I multiply that cos x through on the top, those two little mini denominators cancel, and I'm left with just 1 minus sine x. Now, I'll tell you right now that this is a very special case that we're going to encounter. And I know if I didn't tell you what to do with this, you could look at it for a long time and try a bunch of things, and it would never work. You need to recognize something now. I'm going to go on a little detour. Would you agree that this is the case? Nothing to do with this problem directly just yet, but that cos squared is 1 minus sine squared. Remember, I've told you that you need to know the following things. Well, this is on your formula sheet, so you don't really need to memorize it, but you need to know that sine squared of x is equal to 1 minus cos squared of x, that cos squared is equal to 1 minus sine squared of x, and I think I even said I'm putting a lot of burden on your shoulders. I keep loading on things that you need to know. But you also now need to know the following, that cos squared of x is equal to 1 plus sine x multiplied by 1 minus sine x. Can somebody offer up an explanation as to why that must be the case? Miles?
Sine times sine is sine squared. 1 times 1 is 1 times negative. Yeah. That's how it works. 1 times 1 is 1.
Yep.
Negative sine x times sine x gives you negative sine x squared.
And what about the outer and inner? Why don't we worry about those?
They cancel.
They cancel. In other words, 1 minus sine squared, this thing I'm pointing at right now, this is a difference of squares, and it factors as a difference of squares into the two conjugates. And if you can see that, and you look ahead, replacing cos squared with 1 minus sine squared is just one tweak away from factoring that bottom to cancel the 1 minus sine x's. Right, so we're using a Pythagorean identity here. And I'm just abbreviating. You can abbreviate too, just not on an exam. Just to make it clear, this cos squared of x is the same as 1 minus sine squared. But 1 minus sine squared factors into 1 plus sine x times 1 minus sine x. So these cancel. You don't need to justify this. That's just algebra. It's not a trigonometric substitution. And then we're going to have 1 over 1 plus sine x. This pleases us because that's what the left-hand side is equal to. So the left side equals the right side. And we have one more to do. I don't think we're doing the non-permissible values on the last one. There it is. It does mention non-permissible values or permissible values, but it's just saying prove that it's true for all values of x that are allowed. And this looks intimidating. But every little move we make, every little step we take on that road is an easy step. And every time we take a step, we're going to get closer to the destination. So let's rewrite this. I hope it's clear you're going to have to be working on both sides here. Maybe you're going to have to do more work on the right, maybe on the left. I don't know. Actually, I don't think so. I think the right-hand side is going to clean up very quickly. But let's rewrite it. Sine of 2x minus cosine of x. This is the left side over 4 sine squared x minus 1. The other side, I'll just draw a line down the middle of the page. I don't know how much space I'm going to need. Is sine squared x cos x plus cos cubed x over 2 sine x plus 1. I hope that everybody sees there's only one thing, and I forgot my x here. There's only one thing we can do in terms of identities here. And it's to change that sine of 2x to 2 sine x cos x. That's it. That's all we can do with identities. And that means this. When we first learned how to manipulate trigonometric expressions using identities, and we spent that extra day practicing, that's what you have to do here with both sides. You have to try to clean these up so they become the same thing. Okay, so if we go down that list, and I don't see many people with that pink sheet of paper out, but remember that pink sheet of paper? If you were to look at the back of it, it just says when proving a trig identity, just keep your eyes on the other side. That's it. You're still using the same strategies. So everything's already written in terms of sine and cos, yes? Okay. There are not, on the left-hand side, two fractions that are separate that we can bring together with a common denominator. The left-hand side is a single fraction. which is what we always want. So is the right-hand side. I don't recognize anything flashing at me. Like I don't see a sine squared plus cos squared. I kind of do, but I have to do something to reveal it. The only thing I can do is factor. So this is a test of your algebra skills. For example, on the top of the left-hand side, I can factor a cos x out. There's a cos x in the first term. This is the first term. Plus, this is the second term. There's a cos x in each term I can factor out, leaving me with sine squared of x plus cos squared of x. That makes me happy. Because there's my 1, right? In my next step, I'll be able to say, no, I'm just not going to write it. I'm going to put the number 1, and I'm going to have to explain why. Speaking of which, I should have put double angle identity here. Or again, if you don't remember the names of them, write out the identity you used. Over 2 sine x plus 1. Well, we're so close there on the right-hand side to the end of the road, it turns out, that I'm just going to write cosine of x times 1 over 2 sine x plus 1 because of a Pythagorean identity. Again, I'm abbreviating just to save a few seconds here and there, but on an exam you would not abbreviate. I don't think there's much more we can do with the left or the right-hand side. I'm really curious. How many of you see how the left-hand side is going to turn into the right-hand side? Some of you are seeing it. It's all about factoring. If I factor a cosine of x out, I'll have 2 sine x minus 1. Well, look at that cosine of x I just wrote here. I want that on the top. It's on the top of the right-hand side. That's a good thing. Over the bottom of this is a difference of squares. And I have, again, not to put too fine a point on it, but I always do this, that's a factor because it's in brackets being multiplied by the rest of the top. This is a factor because it's in brackets being multiplied by the rest of the bottom. That means there's a common factor on the top and the bottom, and we are done. I mean, I don't think you should just end it there and say left side equals right side. I think it's valuable to rewrite them in their cleaned up appearance, to rewrite cos of x over 2 sine x plus 1. I mean, everybody and their dog knows that 1 times cos of x is cos of x, but I'm going to go ahead and write it without saying times 1. And now you can say left side equals right side. The non-permissible values are things that you need to be able to determine, but they are less important right now in my mind in your math education than doing the proofs. Okay? And you know, when we first introduced this stuff, it was brand new and it was a blow to the brain. This is not a blow to the brain because it's using everything we've learned, but you still need lots of practice. Okay? And there's no shortage of questions. You can either work with the textbook questions, and I want you to notice I've changed the numbers in the textbook. The numbers that you have in your handout include non-proofs. I've just changed it to the ones with proofs. Or you can work on pages 36 to 39. There's a whole boatload of trigonometric proofs. Number 5 on page 29 of your handout are proofs that involve sum and difference identities. And number 3 on page 33 involve double angle identities.